Hello everyone, this is Greg from ChemCore. This is the Intermolecular Forces explainer video where I'm going to be going over the worksheet available in the description below for intermolecular forces. If you haven't had a chance to try this, look in the description, try this out, look at the answer key, watch this video. If you're not familiar with the topic video is also in the description, just a couple minutes long. Go check that out. In this video, we're going to be discussing intermolecular forces, and the first question is really just asking us, mark all the intermolecular forces present in each molecule and specify the strongest force present. We're just going to write check marks for all the forces present and little star sign for the specific force that ends up being the strongest. The first problem, and to go along with this, I really suggest maybe draw Lewis structures if you're not so quick with seeing molecules in your head. There's absolutely nothing wrong with drawing out Lewis structures to make sure you're correct. I'm just going to speed through these molecules to describe why they have the certain forces that they do. The first molecule, NH3, this is a covalent molecule, which means it does have London dispersion forces by default. So we'll put a check mark here. And then dipole-dipole forces, we should analyze if the molecule is overall polar. And it is. NH3 is overall polar, which means we should have existing dipole forces. And to examine hydrogen bonds, we need to see if hydrogen is either attached to O, N, or F, or NOF. Sometimes I remember NOF. Some people remember FON. But maybe write this on the top. It's going to be useful for the future. Notice that hydrogen is connected to nitrogen, so it should have hydrogen bonds. And interestingly enough, this chart is kind of from weakest to strongest. And so your strongest bond should be hydrogen bonds. It's much stronger than London dispersion and dipole-dipole forces. The next problem, K2S. Notice very slowly, I mean, if you're trying to draw a Lewis structure and you're having trouble to do it, there's a reason for it. K is a metal and S is a non-metal, which means this is an ionic bond. And so none of these intermolecular forces will really exist for this molecule. For ionic molecules, they have ion-ion interactions, called different things in some different courses, but they do not have any intermolecular forces. The next molecule, HCl, is a covalent bond. It is a covalent molecule, so by default, it should have London dispersion forces. And dipole-dipole forces, we should really analyze whether it's polar or non-polar. It is a polar bond. It's a polar molecule overall as well, which means it does have dipole-dipole forces. And to analyze if it has hydrogen bonds, is hydrogen attached to either oxygen, nitrogen, or fluorine? It's not. So we do not have hydrogen bonds, which means our strongest bond is dipole-dipole forces. The next molecule, F2, it's by default a covalent molecule, so it does have London dispersion forces. It is a non-polar molecule, so it definitely does not have dipole-dipole forces. And it does not have any hydrogen at all, so definitely not a hydrogen bonding molecule, which means, unfortunately, its strongest intermolecular force is London dispersion forces. PCl3, it is a covalent molecule, so by default definitely has London dispersion forces. It is also polar, which means it does have dipole-dipole forces, but it does not have hydrogen at all, so definitely does not have hydrogen bonding, and it ends up being dipole-dipole forces is our strongest force. NaCl, interestingly enough, is an ionic bond, right? It's an ionic molecule, so it does not have any intermolecular forces at all, like K2S, like previous. SO2 is a covalent molecule, so by default, again, London dispersion forces, and it is polar, so dipole-dipole forces. No hydrogen, so no hydrogen bonding. Dipole-dipole is our strongest force. CO2, it's a covalent molecule, so London dispersion, but it's nonpolar, so no dipole-dipole forces and no hydrogen bonds because there's no hydrogen at all. So London dispersion forces are our strongest force. I2, similar, covalent compound, so it does have London dispersion forces, but it is nonpolar and does not have any hydrogen, so no dipole-dipole forces and no hydrogen bonds, and London dispersion forces end up being our strongest force over here. CH4, it's a covalent molecule again, so definitely London dispersion forces, but it's nonpolar, and hydrogen is connected to carbon, but that doesn't qualify us for hydrogen bonds, so again, London dispersion is our strongest intermolecular force. CH3Cl, again, covalent molecule, so definitely London dispersion forces, and it is polar. So we do have dipole-dipole forces. However, hydrogen is still not attached to neither nitrogen, oxygen, or fluorine, so this time dipole-dipole forces are strongest. HF, covalent molecule, also polar, so dipole-dipole. And hydrogen is connected to fluorine, so also hydrogen bonding. And hydrogen bonding is our strongest intermolecular force. H2O, covalent molecule, polar. And hydrogen is connected to oxygen, which qualifies us for hydrogen bonding. So it is, the strongest bond is hydrogen bonding. And this is actually, I'll put a star next to H2O because the fact that it has hydrogen bonding makes it such, is one of the properties that makes H2O such a special molecule, and really is one of the molecules that gave us life on Earth. That's a little tangent, just my own curiosity and fascination with water. NO, nitrogen monoxide, is a covalent molecule, so London dispersion forces. It's also polar. No hydrogen, so just dipole-dipole forces are strongest. H2 covalent molecule, but it's nonpolar and hydrogen is not attached to anything else, so we only have London dispersion forces. Calcium oxide, it's an ionic molecule, so this qualifies us for any intermolecular forces. O2, it's a covalent molecule, so definitely does have London dispersion forces, but it's nonpolar and does not have hydrogen, so only London dispersion forces. CH3OH, covalent molecule, also polar, and hydrogen is connected to oxygen, so it does have hydrogen bonding. So hydrogen bonds is our strongest bond. Carbon monoxide, covalent molecule, definitely good. Dipole-dipole, it is polar, so good, but no hydrogen, so dipole-dipole is our strongest force. N2, covalent molecule, nonpolar, so no dipole-dipole moment, and no hydrogens, so London dispersion is our strongest intermolecular force. CCl4, covalent molecule, but this is nonpolar, remember that. From the previous video, we discussed that. And no hydrogen, so dispersion forces is our strongest intermolecular, erased it, is our strongest force. H2S is a covalent molecule, so definitely good with London dispersion forces. And it is polar, so it does have the dipole-dipole moment, but it does not, hydrogen connected to sulfur does not qualify for being hydrogen bonding, so dipole-dipole forces are our strongest intermolecular force. The next structure is CH3CF3. It is a covalent molecule, so London dispersion forces. It is also polar, but it does not have hydrogens connected to fluorine. Even though we do have fluorine, don't get tricked by that. Draw the Lewis structure. You'll see that hydrogens are not connected to the fluorines, so dipole-dipole forces are our strongest force. BRF, covalent molecule, also polar. No hydrogens, so dipole-dipole is our strongest. CH3,3N is a covalent molecule, also polar. No hydrogens connected to nitrogen. If you drew this out, it's a little trick question, you'd realize that all the hydrogens are connected to carbon. So dipole-dipole is our strongest force. C2H6, it is a covalent molecule, nonpolar, so no dipole-dipole forces, and all hydrogens are connected to only carbons, so London dispersion forces are our strongest force. CH3NH2, it is a covalent molecule, also polar, and hydrogens are also connected to nitrogen, which means it does have hydrogen bonding. KCl, it's an ionic compound, so definitely disqualifies us from all intermolecular forces. This big compound is definitely covalent, also polar, and hydrogen is connected to oxygen, so also hydrogen bonding. The next molecule, trick question, it is covalent, but it's nonpolar, and if you drew it out, you would see that all the hydrogens are connected to carbons, not oxygen, so it does not have hydrogen bonding. The next question, the strongest of attractive forces is which type? We talked about, you would be tempted to write hydrogen bonds, but in reality, in the beginning of the video, and if you didn't quite catch that, go back to the topic video and watch that again. In the beginning of the video, I mentioned that ionic electrostatic attractions are the strongest force, even stronger than intermolecular forces. And this is just another name, cation, anion, for your ion-ion interactions. Which of these is the weakest of the intermolecular attractive force, taken individually? What we talked about, dispersion forces are almost very minuscule. They're very, very weak. And so dispersion forces would be your weakest intermolecular force. And notice that we can eliminate covalent bonding and ion-ion bonding just because they're not intermolecular forces. So those are just kind of flack answers. You just don't even have to take them into consideration. Which of the following is not found in the substance? Let's just go one by one. Dispersion forces, it's covalent, so definitely there. Dipole-dipole, it's polar, so definitely there. Covalent, we talked about it earlier, definitely there. Hydrogen bonding, this oxygen is connected to hydrogen, so definitely there. And ion-ion should be your answer. And notice that ion-ion interactions assume that we do have an ionic bond here, which we do not. So definitely the right answer. Consider the following 3 molecules to answer the following questions. Which has the strongest IMF? We can consider hydrogen bonding. So let's think about hydrogen bonding should be our strongest. So which molecules have hydrogen bonding? It's our third. It looks really bad. Let me rewrite that. Hydrogen bonding. It's our third and fourth molecule. This OHs cause hydrogen bonding, so 3 and 4. And the next question is kind of asking us the same thing. Which exhibit hydrogen bonds? 3 and 4. Which exhibit dipole-dipole forces? It's our polar molecules. So this one is polar, polar. This one is nonpolar. This one is nonpolar. And so 3 and 4 have dipole-dipole forces. Which exhibit London dispersion forces? Should be all our covalent molecules. So all of them, 1, 2, 3, and 4. Which are polar? We just talked about that, 3 and 4. Which are nonpolar? 1 and 2. Which contain a zero net dipole moment? Should be the same as nonpolar, right? If you forgot what dipole moment is, check out the previous video on polarity and partial charge. We talk about dipole moment, and it should be 1 and 2. Which contain a net dipole moment greater than 0? Should be polar molecules. Once again, check that video out if you forgot this. Should be molecules 3 and 4. What holds molecules of water together? Notice that this is an intermolecular force. The molecules are being held together. So this is an intermolecular force. And the strongest force that really holds water together is hydrogen bonding. So I'll just write H bonding. And this is the little hint that I dropped earlier in the video when we came across H2O. What holds the oxygen and hydrogen atoms together in water together? Notice that this is kind of a trick question. May seem like the same answer as before, but notice that this is an intramolecular force. This is inside the molecule. And simple enough, it's just covalent bonds, right? Hold the hydrogens and water together. This is the Lewis structures that we've been drawing. Covalent bonds. And we can actually write polar covalent bonds, so just a P. What holds Na and Cl together in salt? Well, in salt, notice that this is like the previous question. You can draw NaCl, right? Table salt. And that's an ionic bond. So ionic bonds hold Na and Cl together. But this NaCl together in a solution, right? These actual molecules are being held together by your ion dipole forces. So ion-ion forces or ion dipole forces. Even you can call them electrostatic forces. There's many names to it, but ion dipole forces. What holds 2 fluorine atoms in F2? This is, again, the same Lewis structure that we've been drawing. This is a covalent bond. And we can draw, it's a nonpolar covalent bond. Just let's be specific. What holds the carbon and hydrogen atoms together in CH4? This is, again, just asking you a Lewis structure. You know, what holds the carbon and hydrogen atoms together? Covalent bonds. In specific, nonpolar covalent bonds. The next question, what holds the carbon and oxygen atoms together in carbon monoxide? Again, draw the Lewis structure. It's literally just asking you what's between the carbon and oxygen bonds. Those lines, right? Covalent bonds. And in specific, that looks really bad. Covalent bonds. And in specific, polar covalent bonds. Let's fix that up. What holds molecules of CH4 together? Well, this is an intermolecular force. This isn't asking for IMF. And the only force present in CH4 is your dispersion forces, or London dispersion forces. What holds molecules of carbon monoxide together? Well, this is also an IMF force, right? Molecules are being held together. And this should be your strongest force present, which are just dipole-dipole forces. Just dipole-dipole forces. This concludes the explainer video for intermolecular forces. If you're iffy on this topic, I suggest go back to watch the topic video and maybe retry the worksheet for yourself. And I will see you guys in the next one.